Ignition sequence starts.
Good morning and welcome to Mission Control Houston and the International Space Station Flight Control Room. This is the spot where a team of specialists is on duty around the clock to keep a close eye on the systems of the station and assist the Expedition 61 crew members as they work through their daily tasks. This week, Commander Luca Parmitano and Flight Engineer Drew Morgan completed the third in a series of spacewalks to install a new cooling system on the alpha magnetic spectrometer, keep that cosmic ray detector operating through the life of the space station.
Houston Station on Space to Ground.
Welcome to Space to Ground. I'm Kayla LaFrance. From spacewalks to visiting vehicles, there is never a dull moment for the crew on board the orbiting laboratory. On Monday, NASA astronaut Drew Morgan and European Space Agency astronaut Luca Parmitano completed the third of 4 planned spacewalks to upgrade the station's Alpha Magnetic Spectrometer experiment, or AMS-2. The duo installed a new pump system, which replaces the aging cooling system the AMS requires to operate its large, powerful magnets. One more spacewalk is left to leak check the new system after it's pressurized, and then AMS can continue its particle hunt well into the 2020s. Traffic around the space station will continue to be busy as the crews prepare for multiple cargo ships and the next commercial crew visit. On Thursday, SpaceX launched its 19th commercial resupply mission to the International Space Station. Dragon is carrying over 5,700 pounds of payloads, including more than 1 ton of samples and scientific research instruments. Highlights include a microgravity fire behavior test and 40 mice for an analysis of muscle deterioration. Be sure to watch NASA TV this Sunday, December 8th, for Dragon's arrival and capture, followed by the installation to the Harmony module. Roscosmos also launched the Progress 74 cargo craft from the Baikonur Cosmodrome in Kazakhstan. The spacecraft will make a 2-day journey before arriving at the station December 9th. NASA TV will begin coverage of the 74P docking to the Russian segment starting at 4:45 a.m. Eastern. Preparations continued for the launch of the Boeing Starliner on its first voyage to the station. Boeing completed a successful wet dress rehearsal this week. This wet dress rehearsal was designed to check out and test the full integration of the launch vehicle loaded with liquid propellant along with all associated ground support systems. Keep sending in your questions using the hashtag AskNASA. We'll see you next week.
To go back to the spacewalks for just a minute, a 4th AMS spacewalk to conduct leak checks around the new cooling system will be scheduled later, and AMS will remain dormant until then. And during some of the tasks on these AMS spacewalks, Parmitano and Morgan made use of a special new tool developed by college undergraduates in the Houston area. Have a look at how the Artemis generation is contributing to NASA's mission right now. Each of these AMS spacewalks began the same way all other International Space Station spacewalks have, with the lengthy process of getting the astronauts into the spacesuits that support them as they float out in the vacuum of space. Want to see what that looks like? Well, here's an accelerated view of the process from this past October when Parmitano helped Morgan and astronaut Christina Cook get ready for their spacewalk. This spaceflight is the first of astronaut Drew Morgan's career, but his 6 spacewalks to date already have him at number 27 in history in the amount of spacewalking time. Floating out that door half a dozen times is quite an achievement, but then Morgan is no stranger to making giant leaps.
I think I often describe myself as a soldier, a physician, and an astronaut. The pursuit of those happened in that order. One of the earliest memories I have is of always wanting to be in the military, of wanting to be a soldier. Quite a history of military service in our family. Both of my grandparents, my father was an Air Force officer, and I also remember my parents telling me a story about my great-uncle Clink, Harry McClintock, who was a paratrooper in World War II. He was in the 101st Airborne Division and jumped at Normandy on D-Day, and then jumped in Operation Market Garden in Holland. And that was the first time I had ever heard of the concept of a paratrooper or what it meant to be an airborne soldier. So when I later decided, I graduated from high school and I went to West Point, I knew that I was very interested in this concept of being an airborne soldier. At West Point, they had a parachute team called the Black Knights. Yeah, so I made the parachute team, and that became one of the central activities of my remaining 3.5 years at West Point. In addition to academics, after class, we jumped most days of the week, but then we were also a demonstration team, so we jumped in football games. Also, while I was a cadet, I went through military basic airborne course, which taught military static line parachuting. Specifically the parachute aspect of it, if I go back to the time when I was a cadet, my teammates that I was selected with became my best friends in the world and continue to be to this day. And that camaraderie that we had and that dependency we had on each other, making sure that we were skilled in the aircraft, skilled in the air, our lives depended on each other to do safety checks of each other, that type of camaraderie is something that I feel now in the astronaut corps with my astronaut colleagues as well. I think about how 20 years ago I was developing those skills at an early age and didn't even know it. I'm Andrew Morgan, and I'm a soldier, a physician, and an astronaut.
International Space Station training doesn't require that astronauts jump out of perfectly good airplanes. But the course of preparation for a 6-month tour of duty on orbit lasts more than 2 years and has its own tough elements. Modern technology allows astronauts to train more safely than in the past as they prepare for the missions of today and those of the future.
Mission training for astronauts has always been rigorous. Testing our astronauts' limits, abilities, and knowledge is still an integral part of readying them for the tasks they'll carry out in space. In the Apollo era, there were so many more unknowns. Those pioneers used the best of what was available to them at that time and invented the rest. Safety was and is a top concern. but we push boundaries at NASA at great risk. Throughout NASA's history, technology has fueled the evolution of our training programs. Virtual reality allows our astronauts the benefit of safely repeating mission-specific events and activities, although some things we do don't look that different from back then. Astronauts have to be prepared for their journeys. It's the nature of all of those who explore.
Now, apart from the AMS spacewalks, the Expedition 61 crew is in the midst of a lot of cargo traffic. A Russian Progress cargo vehicle that launched early this morning should dock to the Russian segment of the station on Monday morning, December 9th. And our coverage on NASA TV and NASA.gov starts at 3:45 a.m. Central Time. And a SpaceX Dragon cargo ship that launched on Thursday is due to arrive Sunday, December 8th. Our coverage begins at 3 a.m. Central on NASA TV and NASA.gov. This 19th Dragon cargo mission has a variety of cutting-edge scientific experiments on board. Here's a look at some of what's due at the door this weekend. Now, also in the area of cutting-edge science, there's a cutting-edge piece of hardware that's being tested on board the International Space Station. Researchers are looking into using 3D printing technology to manufacture biological materials in microgravity. Now, that would allow cell growth to happen in 3 dimensions, and it potentially could get around the problem of rejection of the immune system, rejection of the donor tissue, if the patient's own cells were used to grow the new organ.
Cutting-edge biomanufacturing aboard the International Space Station. Presented by Science at NASA. Most likely, you're aware of 3D printing, which allows you to design and produce one-of-a-kind pieces for a variety of purposes. But what if you could use that same technology to manufacture biological materials, like new tissue or blood vessels? Welcome to the world of 3D biomanufacturing, a cutting-edge practice on Earth that is being tested aboard the International Space Station, or ISS. Dr. Mike Roberts, Deputy Chief Scientist at the ISS U.S. National Laboratory, explains why the space station is critical to biomanufacturing's future. We've been able to grow cells in a lab for well over a century, but gravity limits that growth to 2 dimensions. Cells can grow outward, but not up and down like they do in the human body. Also, lab cells are often in contact with the glass or plastic that contains them. But aboard the space station, our experiments will be conducted in microgravity. That allows you to build your cell models in 3 dimensions, without being confined to the bottom of a dish, or unable to grow in contact with lots of other cells. Biomanufacturing imagines the ability to someday grow a viable human organ. Organs are composed of specific tissue intersected by blood vessels. Most organs and thicker tissues in the body have a rich, complex network of blood vessels that provide nutrients and remove wastes from the living cells that make up the tissue. We currently lack the ability and the tools to engineer these highly branched, living networks of vessels inside layers of tissues on Earth. Another medical advantage to manufacturing biological parts in space is the potential to bypass the body's immune system. Today, organ transplants from donors are prone to rejection because the patient's body perceives the new organ as a foreign object, and their immune system tries to attack it. But with the ability to grow tissue in space, a person could conceivably have their own cells used to make their new organ, which might avoid the body's rejection. 3 different types of biomanufacturing facilities will be tested aboard the space station. 2 of them perform in a manner similar to a standard 3D printer. They extrude cells in layers to build tissue. The 3rd type uses powerful magnets to position the cells in place. Each of these 3 different approaches to bioprinting in microgravity will be available to medical researchers seeking to better understand how to engineer tissues and organs for use in repairing injury and curing disease on Earth. As Dr. Roberts notes, the 3D bioprinters represent cutting-edge technologies that could clearly benefit health outcomes on Earth. I think the ability to manufacture a fully functioning human organ will take some time, maybe a decade or more, but the knowledge we'll acquire to get there will also create interim benefits as we learn more about cell regeneration in space and its application to humans on Earth. For more inside information about studies inside the station, visit www.nasa.gov/ISS-science. For more on science happening on, around, and beyond our planet, go to science.nasa.gov.
The International Space Station provides a working laboratory for astronauts in the microgravity environment, and solar energy is a key element in keeping it running. Astronauts rely on this renewable energy source to power the machines they need for their science work, and to power the ones they need for their survival. In this demonstration video, astronaut Ricky Arnold explains the process of generating power from the station's solar arrays to produce electricity for astronauts as they orbit 250 miles above the Earth's surface.
Hi, welcome aboard the International Space Station. I'm astronaut Ricky Arnold, and I'm currently at one of our human research facilities on ISS, where you can see centrifuges, laptops, and other scientific equipment. Across from me is another one of these experiment racks, where you can see ultrasound imaging, more laptops, cameras, other equipment, all stuff that requires electrical power. In fact, we have so much equipment for science and life support that our electrical system has about 8 miles or 13 kilometers of wiring to make it all work. So where does this energy come from? Let's have a look. From here in the cupola and through other windows, you can easily see the solar arrays soaking in the sunlight. They are massive. These 4 solar arrays are made of solar cells, which are purified chunks of the element silicon. Together, the solar arrays contain a total of 262,400 solar cells and cover an area of about 27,000 square feet, more than half the area of a football field. That's huge. When the station is in sunlight, the solar arrays produce about 60% more power than we actually need during the daytime. That extra power goes directly to charging our lithium-ion batteries. Now, those batteries are essential because they provide the power we need during the 16 night times we have per day here on the space station. The energy our solar arrays can produce is enough to power 40 homes, and we can maximize the power we generate by rotating the arrays in 2 axes. One like a windmill to track the sun through the course of the day, the other to track the sun's inclination, or its angle in the sky. The space station's electrical power system uses direct current to provide energy for our laptops, lights, water recovery system, and science experiments. Thanks for coming aboard today. Now back to Earth.
For all the years that men and women have flown in space, they've taken pictures out the window of their home planet. You saw some of them there in that feature. Well, those pictures, they're amazing. They're remarkable. But for the folks who took the pictures, it's still something of a strain for them to convey to the rest of us Earthlings just how miraculous that view really is.
I had looked at pictures on social media and pictures in NASA archives of the Earth so many times, I actually started to get worried. What if I get up there and it's just like the pictures? I mean, that's going to be weird if that's the thing where I'm like, oh, it looks just like the pictures. I'm ready to go home now. And then on the Soyuz, my launch vehicle, I launched with the Russians. And on my Soyuz, when I first got a chance to look out my little window, which is about right here, at the Earth, there's something about looking out a round window at the curvature of the Earth that makes it just more pronounced and really makes it have a huge impact. I just had this feeling like I was way up high looking down, and we were over the ocean, and the blues that I saw, it was ridiculous. I'd never imagined in my entire life getting to see something that beautiful. It was so foreign for the human mind to look at that, to see the total black of space, to see the Earth highlighted that way. And then I got to see a sunset. I had one piece of paper, it had a picture of my kids on it and a few of my flight data file burn times on it, but I just took a pencil and I drew like 15 curved lines, and I just wrote light blue, darker blue, pink, purple, dark purple, all the way down to the surface of the Earth at sunset, because the scale of looking at a sun refracting through the atmosphere, it blew me away, and no picture captures that. There's no high enough dynamic range of a photo to capture what the human can see. So that first look outside completely sidelined me. I had a GoPro, and I made a recording to my brother of, no matter how much it costs in the future, come do this. You have to come do this. I mean, it's amazing. Over my 6 months in space, getting to look at the Earth every single day, it shows you something different. Every day it shows you that it's alive. It's a being just like we are. We're guests on this planet, and it's our mother, it's our father, it's our starship cruising around the sun in the middle of the solar system. There was never a moment that I looked out the window and didn't immediately grab a camera to take a picture of something that our planet was doing. It always surprised you. It's always magnificent. I'm a pilot, I'm not a scientist, I'm not a psychiatrist, I'm not a poet, but certainly when you're in low Earth orbit, looking down at the Earth, it doesn't matter if you're a physicist, a school teacher, a stay-at-home parent, or maybe you just backpack for your whole life. If you look out, you're gonna have a magical experience in your own way, for certain.
Now, in the meantime, NASA's Artemis program is underway. Now, Artemis is going to return Americans to the moon by 2024 and help us get ready to go on to Mars. Knowledge of the geology of both locations is going to be very important. Earlier this year, the next to last man on the moon, Apollo astronaut Harrison Schmitt, joined astronaut candidate Jessica Watkins in the Johnson Space Center's Moon Rock Lab. These two geologists got together to discuss how what we learned from Apollo is going to inform our efforts in Artemis.
Sample of both sides, but I wouldn't bet on it. Okay, I just got a chunk of that side.
They have what I consider one of the most
Can you talk about kind of what went into your sampling strategy and how you chose which samples to bring back?
The idea was to get as broad a spectrum of new samples as we possibly could, and that turned out pretty well. We did. And in fact, we sampled at least ejecta, melt, what we call melt ejecta, from 3 major basins, maybe 4. We sampled fragments that almost certainly came from the deep mantle. of the moon. We didn't know that at the time. That's only recently that we figured that out. And that we also then added to our broad knowledge and history of these volcanic eruptions that have occurred on the moon over time. Now, when you go to the moon on the way to Mars, Jessica, that education I think you're going to get on the moon will be very relevant to Mars. But Mars, of course, does not have that micrometeorite impact environment that we have on the moon, because it has a small atmosphere, about 1/100th of that of the Earth, and that filters out the small impact. The main weathering process on the moon are these micrometeorite impacts and solar wind spallation of the surface. Solar wind's made up of high energy particles, so they actually erode the surfaces of rocks, as well as change the character of the debris layer on the moon. On Mars, the dominant erosive force is wind.
Yep.
And so if you're used to studying geomorphology here on Earth that involves wind,
you're in good shape.
You can learn a lot about what you're going to see on Mars. But all of that comes from studying the moon.
Right.
If we hadn't had the moon, we wouldn't understand this early history of the Earth, or even speculate about what it might be, speculate intelligently anyway, about what it might be.
If you'd like to get another look at any of the features we showed you today, you can. You can check us out on YouTube or on Facebook. There are the addresses right there in the little blue box. While you're there, be sure to look around. You will find lots of other cool stuff about NASA and America's human spaceflight program. If you're out on the internet anyway, you could also check out Houston, We Have a Podcast. That's where we talk to folks about their work in all aspects of space exploration, including human space exploration. We post new episodes every Friday, and today we share a special opportunity we had earlier this year to talk to one of the 4 Apollo moonwalkers who's still with us. On this day, today, before the 47th anniversary of the launch of Apollo 17, Gary Jordan talks with the second-to-last man on the moon, Harrison Schmitt. Yeah, the same one you just saw. What a coincidence. Go to nasa.gov/podcasts for today's episode. It's where you'll also find all our previous episodes and the full library of all of the NASA podcasts, all of which you can also listen to on Apple Podcasts, Google Podcasts, and SoundCloud. This is Mission Control, Houston.